first equation here. So you have velocity squared divided by 2g, g is gravity acceleration. Then you have plus pressure divided by rho g, that's then the pressure contribution, and then plus z, z is the vertical coordinate in the direction of gravity. So this gives you the energy at location 1, and this is equal to the same term at location 2 plus losses between 1 and 2. So H1 dash 2 determines the losses between these two cross sections. And Vm is the mean velocity, P is pressure, I already said, rho is density. And without viscosity, if you had invested fluid, there would be no losses. So that would be simply from Bernoulli equation, energy at section 1 equal energy at section 2, but due to the viscous terms, viscosity, friction at walls, we have these losses. If the cross-section is constant and compressibility effects are negligible, then velocity doesn't change in a pipe or duct due to continuity equation. And if the pipe is horizontal, then losses are seen simply as a pressure drop, because then the velocity term is the same on the left and the right, so it cancels out. Z is the same, and you would simply have a pressure loss. Pressure difference between 1 and 2 corresponds to the losses due to friction. Okay, and if you have a closed loop, and usually, let's say if you take your heating in a house, it's a closed loop. You have a pump, it pumps on one side, and on the other side, the fluid comes back after it has heated the rooms. So you have a closed loop, and what the pump provides is a pressure jump to cover all losses. And if you somewhere close the valve, you increase the resistance, losses are increased, and the pump will still give you the same pressure jump, but then the flow rate will be reduced because of higher resistance. Here's an example of flow from a reservoir through a pipe going out into atmosphere, and all losses are proportional to velocity squared. And line losses depend now on the length and diameter of the ratio of the length to diameter of the pipe, and local losses depend on what kind of local loss it is. So for local losses, we have a certain coefficient, which is empirical pressure loss coefficient, CL, times velocity squared divided by 2G. And for line losses, we have a lambda, which is friction coefficient, and then L over D, that's the ratio of length over diameter, and then again V squared divided by 2G. So in this particular example here, if we consider, let's say, a long pipe, and we have flow going from a reservoir, which is large enough so that the height in it can be considered as constant, we have a local loss at the entrance into the pipe. We have sharp corners, so there will be some locally incurred pressure loss. Then we have a line loss over the length L, and then we have a valve which is in between somewhere. And if we plot this energy line, so total energy constant, but locally we have a grade, we have a slope, and there is a drop at the beginning, which is proportional to C in German now, which means entrance loss. Then we have a straight pipe, so it's then a line with a constant slope. Then we have valve, where there is again a sudden drop proportional to the coefficient CV, and then there is the rest again as a straight line. So this is a simplified approach, and in these kind of methods, the simplest one-dimensional methods, the straight piece of pipe is considered as just one element. There is no other discretization applied. But we will show later that in some of these one-dimensional methods, the pipe is discretized in smaller segments, and each one is a control volume. Then, like in three-dimension, only it has some special features that I will mention later. Now, local pressure loss coefficients, they depend on the shape of local cross-section variation or bend or whatever, and they are usually determined experimentally, but they can also be determined from a CFD simulation, as I already mentioned. And CFD simulation can also be used to optimize these shapes. But for example, if you have a bend, as I will show soon, you can have a bend with 90-degree sharp corner. You can also have a bend which has the same cross-section, but you can also modify the cross-section to minimize the losses. And in many of these pipe or channel networks, whether it's air conditioning or heating or whatever, you have a lot of local losses, and they sometimes dominate or take a large portion of the losses, and they can be minimized by using CFD simulation. For example, you can change the shape of bends, you can avoid sharp edges, apply rounding or other modifications to minimize the losses, and that can be significant. Very often things are made in a certain way because it's simpler to manufacture, but about 20% of the energy that we use is spent on pumping something through pipes, and this could be, by optimizing these pieces, one could save a lot of energy. These coefficients I've given here only a few for an elbow, which is 90 degree, or for T-branch, 180 degree turn. You see they are of the order of 1, so 0.9, 1.8, 2.2. Valves, depending on which valve, let's say the classical valve, which has a complicated shape, even if it's open, it has this CL10. If you have a sliding valve, it just has a, I don't know how to call it in English properly, you have simply something that slides vertically across the cross-section. If it's fully open, there is a small resistance, CL is 0.19, but if you have something like this and you open only 1/4 of it, you have very large coefficient, which is 24, which is then due to the high recirculation. Here's an example of this local loss and how it can be optimized. It comes from a company called MTU, which builds large engines, so let's say for ships and for other applications. And of course, this engine requires oil and fuel and so on, and it has a lot of branches. And there was the requirement at one location to go from one cross-sectional area to another cross-sectional area with a 90-degree difference in flow direction, and diameters are given. And now the question is, how do you form the pipe bend between these two cross-sections? So you see under the word simple, you see the picture, there is one upper circle, cross-sectional area, lower circle, and in between you're free to do whatever you want. So if you simply scale the circle and sweep it along the middle line, that's the simplest shape, but this is not the optimum. Even worse would be 90-degree sharp corner. The middle row here under empirical shows the shape determined by MTU experimentally over 75 years of experience. And CFD optimized is, under CFD optimized, you see the shape that has been determined by using CFD and software that does the optimization. So you specify parameters. We will talk about it in the last set of lectures. You have to create a parameterized geometry in which you determine which parameters are allowed to change, which parameters define the geometry. So it would be like mean radius of curvature of the flow direction, and then you can specify that you have elliptical cross-section, and then you specify for the two dimensions of the ellipse what is the allowed range. So you define geometry with a few parameters, and then the optimization software varies these parameters and looks for the optimum. How the optimum is determined? Well, there are two quantities that need to be optimized here. One is the pressure loss, so you have to minimize the pressure loss from inlet to outlet. And the second one is the homogeneity index, so you want the flow to be as uniform as possible. Of course, if you take the simplest bend, you will get recirculation and strong secondary flow. And if you come with a nicely uniform flow at inlet, you will have a highly non-uniform flow at outlet, as we will show in some future lectures what it looks like. And this is not optimal. So how is this uniformity index, exactly how was it specified here? I'm not 100% sure, but it is something similar to deviation of the velocity from the mean. And you want this deviation to be minimal. So this homogeneity index 1 would mean that the flow is simply uniform across the cross section. And you see here that this simple shape has a large pressure drop, 47 millibar. The experimentally optimized has 15, which is only 1/3 of it, and computationally optimized 14, a little bit better. And if you go 5 diameters further downstream and take the pressure drop, then the experimentally optimized one has a pressure drop of 25 and the computational one 22, so it's better. And the homogeneity index is 0.51 for the simple shape, so a large deviation from uniform. The experimentally optimized one has an index 0.86, so the optimum would be 1.0, and the computational one has 0.87. So you see, it's a small improvement compared to the empirical optimization, but as I said, empirical optimization took many years to develop by small increments, and the software can help to obtain optimum much faster. And now if you imagine how many 90-degree bends are in a pipe network in a big house with 30 stores, you can imagine also how much energy could be saved if every bend was manufactured such that the pressure drop is 3 times smaller. Okay, so that was a simple example, but very often these pipe networks or duct networks for air conditioning, they are very long, they have many loops, and these loops are interesting because they interact with each other. So in the simple example shown here, we have one supply pipe, it comes to branching point A, then you have 3 more pipes, and then they come together in point B, and these flow rates for individual branches, Q1, Q2, and Q3, they will now depend on how long the branches are, what are the cross-sectional areas, what are the possible obstacles in their valves or whatever. So you can increase local loss by, let's say, partially closing the valve. That will reduce the flow rate in that branch, but then the flow rate in other branches will increase because of continuity conditions. So for all of these branches, we have the continuity condition, which says that the sum of inflow must be equal to sum of outflow. Sometimes you have a branching point where from, let's say, 2 pipes come in, bring the flow into the branching point, and then 3 or 4 are going out. So that everything that comes in must equal what goes out. And then if you take a branch that connects the same 2 nodes, then the same pressure loss must apply. So here, this means that the pressure loss from point A to B is the same whether you go along the branch 1, branch 2, or branch 3, because at the end it's the same point. And these conditions are used then to do the dimensioning or to compute the flow rate. So how would you determine flow rates in branches 1, 2, and 3? Well, you would first of all, you have to use an iterative procedure. This is why I'm using this example, because it shows that even for such a simple example, you have to iterate. And our CFD is practically all about iterations to find the final solution which satisfies all equations. And here's the simplest example of an iterative approach. you guess the flow rate through the pipe 1. So if you know the flow rate Q that comes from the main supply to point A, you could first assume that it splits into 3 equal parts. So you start Q1 is 1/3 of Q. Then you compute the pressure loss for the pipe 1, taking the parameters I mentioned earlier, friction coefficient lambda, a length of the pipe diameter, and any local losses that you may have. When you sum all of them, you will get a pressure loss for the pipe 1. Now you know that the same pressure loss must apply to pipes 2 and 3. And for the pipes 2 and 3, you will now take the pressure losses given and compute the flow rates. And now you get flow rates Q1, Q2, Q3, and they don't add up to Q. Now you have to make the correction to the Q1 that you first estimated as 1/3, and then repeat this procedure. And if the procedure is designed properly, it will converge. It means you will get at the end situation where the changes to flow rates will be minimal and everything will be satisfied. So the iterative procedure is then based that you check the continuity constraint. After the first step, you find that the flow rate, that the sum of the flow rates through the 3 branches doesn't equal the flow rate that comes in. And now you correct the flow in the pipe 1, and the correction is usually such that if you over-predicted the flow rates, you will reduce it. If the sum of Q1, Q2, Q3 is smaller than Q, you would increase it. And the increase or reduction can be the ratio of the incoming flow to the outcoming flow rates. And then you repeat the procedure, and this works, and usually it converges. Now you can do it by hand for small networks, but for large number of loops, for large networks such as the piping system in a big house, you would need to use a computer to do this. You need a computer code to do it. In more complex situations, like on the right at the bottom of this page, you see, for example, a gas network in a city, and there are many loops, so there are connections from one street to the other and so on. And the additional constraint in these loops is that the pressure drop, if you sum it along all pipes going in a loop in either clockwise or counterclockwise direction, the sum of pressure drops must be 0, because you will come back to the same point. For example, if you take this loop, which I labeled J, you first have the pressure drop on pipe that goes from node 1 to node 2, so P2 minus P1. Then you go next pipe, which goes from node 2 to node 3. So you add to it P3 minus P2. Then you go for the other pipe, which goes from node 3 to 4, then from 4 to 1. And now you close the loop. And obviously, because you started from node 1, then you come back, all these will cancel out. So you have P2, once with positive, once with negative, and all of them, they will cancel out, and you have 0. So in an iterative procedure, you will have to enforce that the pressure drop over every closed loop is 0, and you have to also enforce that in every branching point, the continuity equation is satisfied. And if there are any losses of fluid along these pipes, because very often small, let's say, individual gas consumers in a city gas network, these branches will not be taken into account. There is simply assumption that there is certain number of connections, and they will be distributed like a continuous loss along the pipe. But this also needs to be taken into account. And these methods, which don't discretize the pipe but consider it as a single piece, are usually computed using Hardy-Cross method. This is a popular method that's used in most codes that simulate these one-dimensional gas networks or oil pipelines and so on. So they first have to identify all independent loops in a network. This can be tricky. If you do it by hand, it's usually complicated. If you enter the data about the network in a computer by numbering all nodes and then numbering all pipes and defining for each pipe the nodes on the left and on the right. Then there are computer codes based on graph theory, which flow rate is cross-sectional area times velocity and times density, and so and C is the coefficient which then represents the sum of line and local losses. And you now say, okay, I have to correct this flow rate by certain delta Q, and I have to apply such a correction in every pipe, but I shouldn't destroy the continuity constraint in every node. And in this expression, because velocity squared is pressure drop is proportional to velocity squared, when you take the square of Qi plus delta Qi correction, usually this delta Q squared is neglected because it's second order in correction. All correction tend to zero as the process, as the iteration process converges, and this delta Q squared goes to zero faster than the term in the middle, which is 2Qi times delta Q. And then for every loop, you can write that the sum of these delta Pi's for all pipes should be zero. And because you have here two terms, you can compute this delta Q for each loop, for each pipe in the loop. The correction that you apply to each pipe in the loop, which will then not destroy the continuity constraint because the same correction is applied to every loop, but it will improve the pressure distribution. And if you repeat it many times, you can get solved solution, converged solution. So I won't go into more details here because this is not CFD per se, but still it's interesting, I think, to let you know how these methods in principle work. And one more point that I want to bring to your attention: when these pipes are considered to have a continuous loss of mass along the pipe length, one needs to take into account that some pipe may have supply from both ends. So the flow is not going from node 1 to node 2, it's going from both nodes towards the middle, and then somewhere in the middle you have flow rate 0. A simple example of this I have in my garden. So I have small piece of the garden, I have strawberries, and I have pipe which brings the water there, and then I have pipes which has many holes. So every 20 centimeters or 30 centimeters there's a hole, and I made simply a circle. So the pipe is closed. But then when I let the water come in, water drops from every hole, and somewhere between two holes there is a zero flow rate, so water comes from one side and then comes from the other side, and one pipe is supplied from the right, one hole is supplied from the right-hand side, the other hole is supplied from the left side, and in between there is no flow rate. And there was one publication in which this was discovered, and this solved many problems, convergence problems that other codes that do similar things have. So that's all about the simplest methods which don't discretize the pipe. Now the next level is that we do discretize the pipes using control volumes, but there is only one control volume for the whole cross section. So there is no, it's like beams in finite element methods. If you are familiar with them, you don't discretize in the cross section, but you discretize along the pipe. And so every pipe control volume has two faces from which there is a flow, so in left and right. The rest is wall, and the velocity at cell center is then the mean velocity over the pipe. So you have to determine the wall shear stress for the balance of momentum using some empirical correlations which links the wall shear stress to the mean velocity of the pipe. And these empirical correlations can be, for example, determined using the methods that I will show in the next part, where we compute the fully developed flow in the pipe, and that is what's usually assumed in these methods, that you take now shear stress relation to the mean velocity from such detailed simulation. And then this is here applied as known. Now all these 1D cells are connected at branches, and these branching multidimensional elements, they need to take these methods into account that I mentioned earlier, continuity and closed loops and so on. So, and one can connect these 1D methods with 3D methods if you, for example, have a branch which is treated in 3D sense, and all straight parts are treated using these one-dimensional elements. So, no more details on 1D. If you are interested, I encourage you to have a look at some of the codes that I mentioned here. One is GT Suite that comes from the Gamma Technologies company. It's used to simulate flow, hydraulics, lubrication, friction, and so on, especially in vehicle, for vehicle development, thermal management, and so on, but also for powertrain, for hydraulics, and so on. And they use it also nowadays for multi-body mechanics, for engine performance simulation, and so on. These 1D codes, they all require calibration. We talked earlier last time about errors, and as you can imagine, in these one-dimensional codes, modeling errors dominate. But also, you could say also discretization errors, because it's only one control volume typically per pipe. But the errors are usually relatively large, and they need to be calibrated. So in order to get useful results, you need good calibration. And this is the main problem with these codes, that if they are not calibrated properly, they will give you solution, but it may not be trusted. And this is something that one has to be aware of. Another popular 1D software is Wave. It comes from Ricardo. It's a British company. And they are also used for engine performance, but also used a lot for acoustic and noise, for simulation of combustion and emissions, real-time engine simulation, and so on. They also have a 3D code, so they perform, called Vectis, so they perform also 1D, 3D code simulation. And finally, there is called FlowMaster, without W. Formerly it was FlowMaster. It comes from a company called Mentor, but that has been bought by Siemens 2 years ago. But they still have their own web page. So if you go to this web page, you will see Mentor, but under it is written a Siemens business. And I think during the next year that will be fully integrated into Siemens. So next year you will find this software under Siemens, just like Star CCM Plus. So Siemens is expanding into many areas, and this is now an addition. So they first bought Syria Dapco to buy Star CCM Plus for 3D flow analysis, and then they bought Mentor for one-dimensional flow analysis. Now Mentor does also some other things, but Siemens paid for Syria Dapco $1 billion roughly, and for Mentor $5 billion. So there is even more business in simpler analysis than in detailed analysis. And there are several other, both commercial and maybe also some open 1D course, which I will not go into more details, but as I said, if you're interested, I encourage you to have a look at these 3 websites. I don't want to do advertising for any of them, but depending on the application, they all can do the job correctly. Okay, so this was basically all. Conclusion is that 1D simulation is used to predict performance of complete system usually, so it's a system analysis. They are often called system tools. You can't do this in real CFD with 3D analysis. That would simply be too complicated. Elements of network which involve complex 3D flows are represented by empirical, so-called lump sum model. And these models are derived either from experiments or from detailed CFD analysis. The performance of such system usually depends strongly on these non-pipe or non-channel components, because calibration of a straight pipe or straight channel is accurate, so there is no uncertainty about that. Optimization of network requires optimization of components and their interaction, and that will then inevitably require some local 3D flow analysis, as I showed for this example of a bend. So if you want to optimize something, there is nothing to be optimized on a straight pipe segment. If you do optimization, it has to be with other pieces which include local losses. So that was about 1D analysis. I suggest I go with the next presentation, then we can do questions afterwards, unless there is something urgent that somebody needs to ask immediately. Let me see, I don't see anything in chat and nobody is saying anything, so...
Well, Professor Pirsch, I would have a small question to these slides, but we can do it afterwards, whatever you like.
Well, you can ask now, no problem.
Okay, on the 6th slide, I think, where you have shown the pressure loss coefficients, what is the difference? What is the difference between the open valve and the open slide valve? Again, I didn't catch that.
The normal valve is, if you, I should have shown the picture. The usual valve has pipe on the left, pipe on the right, and then in the middle is a complicated shape with a conical thing that goes and closes the valve. So the flow around this valve is very complex, and it has a large resistance even if it's open, because the flow has to go around this valve body. The slide valve is a Schieber in German. It's just a plane. So when this valve is open, there is basically nothing in there other than these edges where the sliding piece goes into when it's closed. So there's only small resistance due to these edges, but basically there is nothing in between. The same is if you take ball valve. Ball valve also usually has opening in the middle, so when you make it fully open, there is basically no resistance in that case. It's like a straight pipe. But if you take a ball valve and open it only a little bit, then you have a very small entrance, then large volume inside the ball, and then again a small cross section where the flow goes out with large resistance due to edges. So ball valve would have very high resistance if it is quarter open, but these valves, both ball valves and slide valves, they are very good if they are usually only in closed and open position, because if it's closed, no flow. If it's fully open, very small resistance. But in between, they are then worse than the classical valves, which have this conical closing part. They have always resistance, but they are then not so sensitive to small variations in open. That was the point.
Yeah. Okay, thank you. And I would have one more question for the next slide. Optimization? Yeah, right. It seems like the cross-section separation in between the inlet and outlet gets larger. Is that a reason why this works here? What was the fluid going through there? Was it a gas or a liquid?
I think it was liquid, and I'm not sure whether the cross-sectional area gets larger, but it gets elliptical and it is squeezed. So basically what you achieve is that you go from circle to ellipse, which is very has very large ratio of the long to the short leg, and this is why there is no strong recirculation, because the recirculation would happen in the cross-sectional area. In the middle part, you would have half flow going backwards, because the flow would tend to go to the outer end straight, and then will be by pressure forced to go along the other direction. You have strong recirculation. So this squeezing makes it that you avoid this recirculation. And actually, many of these 90-degree bends that you have in piping, they are produced by casting. And to cast this optimal shape is no more complicated than to cast the simplest 90-degree bend. So this could be actually manufactured and used as a mass product, but in most cases, if you go to Baumarkt and want to buy 90-degree bend, it's either 90-degree without any rounding or simple round, but there is usually no optimization.
Yeah, so the area where the highest pressure appears, which is at the 90-degree angle, it gets large in this area, right?
That's right.
You have a highest pressure along the and this makes the flow, and it recirculates much less, becomes more uniform. Such simulation. Maybe it would be good to do it as because it would be a nice example. This was done 10 years ago by Friendship Systems, but it could be, I think, relatively easily repeated. I don't have the same, fortunately, but it can be created, I think.
Yeah, thank you.
Okay, then I close this or minimize it. And we go now to the next topic, which is flows in channels and pipes. And we will see some important features of both simulation software and the flow. Now, the pipes and channels, as I said earlier, appear in many technical applications, and the purpose is either to transport fluid or heat. So you have to, this is the usual application of these ducts and pipes and so on. And if you want to do optimization, we either have to minimize pressure loss or maximize heat transfer. And very often you have to do compromises, because if you want higher heat transfer rate, you would need higher flow rate, but higher flow rate will increase pressure losses. That is, you will need more pumping power, and so you have to make a compromise somewhere how much pumping power you want to afford, and then for the given pumping power, you want to maximize the heat flux, for example. And very often there are space constraints which can be limiting the possibility of geometry optimization. For example, the 90-degree bend that I mentioned earlier, if you wanted to get higher, more homogeneous flow at the exit and smaller resistance, you would need to, make larger distance between inlet and outlet and so on. But very often you have a limited space, so this space limitation is what is always constraining such optimizations. And so what we can see as a basic flow phenomena in these piping or duct systems is that you may get flow separation locally, and you may get secondary flows. We will mention separation today, and secondary flows will be topic in next slide. Now, both of these can be sometimes desired, but usually they are undesired, because I will mention later features which come up. So here are sketches of some important or frequent components in internal flow passage. So you have a duct or pipe with an expansion, like a diffuser, or with a contraction, which is like a nozzle. And then it can be symmetric or asymmetric. You may have a sudden expansion, a sudden contraction, which are a special case of the upper ones. And you can have bends or branches, as you see here at the bottom. So these are the things that we are concerned about, and these are usually ones that need to be simulated, because you can do, of course, measurements, but then you doing measurements for building models for every of these is a little bit complicated. Now there is a book I forgot to mention earlier by Idelchik, that was a Russian scientist who has a thick, big book which has information about local losses at very many different configurations. So if somebody needs to look for these, then Idelchik, if you remember the name. I think I mentioned the name in the previous slide. There is a new publication which is basically copied and translated, but one can find this useful sometimes if you need to determine what is the loss without doing CFD. Now, a special situation in these pipes or ducts are fully developed flows. And I want to mention this because this is very often used for different purposes. Now, a fully developed flow is obtained when the pipe or channel is long enough, which means that the boundary layer which starts growing at the wall when you, let's say, enter from a bigger reservoir, bigger cross-section into a pipe or channel, you first have a boundary layer, it grows, and at some stage this boundary layer growing from all sides, they will meet in the middle, and then there is no more space for the growth. So this state then remains frozen and is then the same all along the pipe. So that means once you reach this fully developed state, the velocity distribution is the same, doesn't change along the pipe anymore, only the pressure reduces due to friction, and if the cross-section doesn't change, then this pressure reducing is linear, because if you look at the Navier-Stokes equation, you will see that the pressure term is linear, so there is no pressure squared there, it's linear pressure. So if velocity is the same, then the equation will tell you that due to the shear, pressure will vary linear. Now, fully developed flows, you usually don't need to compute with CFD because there are empirical data in the books, but this data is usually only mean, and sometimes we need detailed velocity distribution, for example, to use it as inlet condition to a more complicated geometry. For example, if you want to study, let's say, optimize the valve for an engine, it's often put into a test rig where you have an annulus at the entrance cross-section, then you have a complicated flow around the valve seat, and then you have a straight pipe as the exit. And then if you don't know what the flow looks like in this annulus, you compute the fully developed flow and apply these profiles at the inlet. And this is where fully developed flows are very often used. You can obtain a solution for fully developed flow either by using a long enough channel or pipe, and you start with constant velocity at inlet, and then you compute until you get a velocity profile which doesn't change anymore. Or another option is that you take a relatively short channel, put only 2 cells in the axial direction, and apply periodic boundary conditions at inlet and outlet with a prescribed flow rate or pressure drop, and you will get a fully developed solution again. But let's have a look first in the first example, when you start with a constant velocity and then you go and compute over the long enough distance until you get profiles which are not changing. So here is first laminar flow, Reynolds number 100, Reynolds number based on mean flow and hydraulic diameter of this channel. And what you see in the upper picture is the pressure, and you see there is a very sudden pressure drop near inlet, but then later on the distance between these contours which show the constant pressure becomes the same. So you can imagine that pressure is linear. The next picture in the middle shows shear stress. So you see near inlet that there are some variations, but later on it's just the same picture at any cross section. When you look at the velocity vectors, which now don't show the whole channel, only a small part near inlet, you see when you start with the constant velocity at inlet, already in the center of the first control volume, you will see that this constant velocity has changed because of no slip at the wall. Means zero velocity at wall. You get very strong gradient near wall. So in the middle, the velocity is still constant. Then you have a small increase near wall because as the wall applies resistance and zero velocity at wall, then the layer near wall needs to accelerate relative to the middle part, and that's why you have this small peak in the beginning. But then later on, this profile develops, so the boundary layer grows that I mentioned, and these two boundary layers will meet somewhere. And then if we look at the bottom right picture, which is now a little bit stretched, we see now a parabolic profile in the center plane, which repeats, so there is no change in the axial direction anymore. Now, how long this channel needs to be to compute the fully developed flow depends on the Reynolds number. So for this laminar channel, obviously this was here too long. I could have used shorter channel to get the fully developed flow, but for turbulent flow, it's a little bit longer. Now here is shown pressure variation along the duct, so upper right picture. You see at the very beginning very sudden drop, and then relatively quickly we obtain a linear curve which shows that along the distance pressure varies linearly. If you look at shear stress, at the bottom left picture diagram, you see a very sudden reduction of shear stress over the wall over the very short distance. So after half a meter, you have almost reached now constant shear stress, which doesn't change any. And that's why I showed here also again the velocity vectors. This high shear rate at the inlet is due to specifying constant velocity. So if you have a grid here, which I didn't show, but there is every velocity vector is basically in the center of one cell. So you see how many grid points are there. So you have constant velocity in every cell center at the inlet, and then from this first cell center it goes to zero, the wall, and then the next cell already will feel the wall presence, and velocity near wall will reduce. But in the first cell you have the highest gradient, and because shear stress is viscosity times gradient in the wall normal direction, that's why you have extremely high shear stress at the very beginning. If we go to turbulent flow, then this development takes longer. So I use the same duct 10 meter long. I remember cross section was I think 0.1 meter. Then it takes longer to get fully developed flow. And you see here this on pressure distribution. So at the beginning, the distance between these pressure contours is smaller because the pressure difference between two contours is always the same. But then later, from some distance further downstream, you get again linear variation. And in the shear stress, you also see that there is a little bit longer distance over which shear stress varies. You see this red only near the inlet, and later on there is much less variation. You see also that the shear stress is very small in the corner and is maximum at the center of the side of this channel, which is a typical behavior because corner is, there are two walls which slow down the velocity, and near the side there is only one wall. If you look at velocity vectors near inlet, I specified inlet constant velocity, and you see the flow is more or less constant in the middle part of a longer distance, but the boundary layer near wall is developing a little bit slower and takes a little bit longer distance. But at the bottom right picture, we see what the velocity profile looks like when it is fully developed. And you see that it is now more uniform. It's not a parabolic profile with maximum, well, it still has a maximum in the center, of course, but the variation between the mean velocity and the maximum is only maybe 10 to 15%, whereas in the laminar case, it's a factor of 2 in a plane channel if you have only 2 walls, and if you have 4 walls, it's even more. So this turbulent profile is much more uniform, and you have much higher gradient near wall. So the velocity increases from 0 at wall to a certain velocity near wall over a very, very short distance. So this is a typical feature of turbulent flow. Now, turbulence models and how to simulate turbulent flows will be covered in a separate lecture, which will be in 2 weeks from now. But here you have to take it for granted that there is a certain turbulence model used. Here in this case, it was the default K epsilon turbulence model from Stasi CM+. And here Reynolds number was 100,000, so the flow switches from laminar to turbulent somewhere around 2,000 roughly. And in this case, you see also that the pressure variation becomes linear after some distance. Shear stress is also maximum at the beginning. And you see that here, this is taken along a certain line along the wall. So there is somewhere a minimum, then it increases again, overshoots, then settles down, and then from somewhere like 7.5 meters distance, it becomes constant. And this means that we need about 70 channel heights length of the channel to get the fully developed flow. So it takes long. Now, the other approach is to take, and this is what you would normally do if you need fully developed data to use for something, you would take a small part of the channel, just 2 cells, and apply periodic conditions. But here you can make this channel length different. So I showed you here examples to draw your attention to the fact that one needs certain length to get good result. I have here 4 different lengths. It's always only 2 cells. It's the same flow rate specified, but in the upper left picture, you see a very short channel, extremely short. It's only a small fraction of the diameter or the height of the channel. And then there is a bit longer one in the middle. Upper right one is sufficiently long channel, which has the length equal to the height. Or if you have a pipe, the length would be same as pipe diameter. And then at the bottom is one which is longer than necessary. But if you look at the scales, the velocity scale, for the middle one, the sufficiently long and the longer than necessary, we have the same maximum and minimum velocity. So it means the solution, fully developed solution, is the same in all of these cases. But the first one, it has different numbers. So the first one did not converge to the same solution, and as I will show later, it also has convergence problems. Why? Because this fully developed condition that we imply, which means I want to have the same velocity profile at inlet as at outlet, or outlet as at inlet, and I want the same flow rate. But this is not unique because the flow direction isn't specified. So if we would want to have a unique solution, then we will have to specify that the velocity in the cross direction is 0, and that only one velocity component is allowed to change, but because in most codes this fully developed condition is applied also in the periodic condition is applied in situations when this is, the flow is not fully developed. So you have to allow that other directions can also change. And that's why we need certain lengths so that these walls, parallel walls, enforce the flow to be in one direction. And if you take it too short, you may not get the right solution. And you see here for the convergence properties, for very short channel, it converges, but it takes very, very long. And after 800 iterations, residuals are still pretty high. If I take sufficiently long channel, which was the third in the row, I have some oscillatory convergence, but you see after 750 iterations, the residuals have been reduced 6 orders of magnitude. So this is an accurate solution. So this is what I wanted to say here, that you need a good choice is to take the channel length equal to the height, or pipe length equal to the diameter. Now the same exercise for turbulent flow, again short channel, sufficiently long and very long. The scaling is a little bit different, but you see again that sufficiently long and very long channel have almost the same numbers in the scale, not exactly the same on the last digit, but usually almost the same, whereas the short one has a significant difference, much larger difference between the numbers. And this is for the same reason. It's simply too short, and the sufficiently long one is one which you should select if you need fully developed. Now a few words about invested flow. Many methods have been developed in the early stages of CFD to solve potential flows. Potential flow is an invested flow which is in addition irrotational. So you have to impose to invested one more condition, and then you can describe, you can reduce Navier-Stokes equations to a single Laplace equation that describes the flow potential. But these flows have the largest modeling error, as you can imagine. Then the next level is Euler equations, which are invested flows, but they are not necessarily rotational. And this is basically what you get from Navier-Stokes equation if you set viscosity to 0. So any CFD code can be used to compute invested flow. You just set viscosity to 0, and you will get the invested flow solution. Now, invested flow doesn't stick to wall, so at the wall there is a slip condition because of the missing viscosity, and the only thing that the wall does, it's a constrained surface. So it means the flow must be parallel to wall. It cannot cross the wall, but there is no friction and no boundary layer there. The results are often not realistic. As I said, the modeling error is large. So there's no pressure drop in tunnels and pipes, no force on submerged bodies, so this is obviously totally wrong. What the invested flow does show is the qualitative, the relationship between pressure and velocity. So like basically what the Bernoulli equation gives you, if you have increasing velocity, then pressure will decrease. If the velocity decreases, pressure will increase. That's the only thing that you get from invested flow. But still, let's have a look at some features, and then you get a better appreciation of what happens in viscous flow. So this is invested flow through channel with a semi-cylindrical obstacle. Okay, I see this is one slide where I forgot H. So width, not width, but width, a semi-cylindrical obstacle. You see computational grid in the upper picture, and the pressure distribution in the lower picture. And pressure distribution for an invested flow should be symmetric. It looks almost symmetric, but you will see later on when we take the values along wall that it's not quite symmetric, but relatively good. So you have maximum pressure at the front stagnation point, but then there is almost the same pressure at the back, and the minimum pressure is at the top of the obstacle. So what you can read from this is that as the obstacle reduces the cross-section by a factor of 2, mean velocity has to increase by a factor of 2, that you know from continuity. And this shows now that the pressure will not be uniform. Here you will have minimum pressure at the top of the obstacle, and maximum pressure in this cross-section will be at the upper wall, which is straight. You see also that there is a reduction of pressure along the straight wall from kind of brown or orange to green, and then increasing again. Along the bottom wall, you have first increased pressure until you hit the stagnation point, then a rapid decrease until you reach the minimum cross-sectional area, then again rapid increase at the end, and then a little bit of decrease again. So the velocity vectors, they are similar but the opposite to pressure, where velocity goes to 0 at stagnation point, pressure is maximum, where velocity is maximum at the top of obstacle, the pressure is minimum, and then at the end again the same. So you see here visualization of velocity vectors by using arrows, or below the flow pattern is shown by the so-called line integrals convolution. So it's kind of streamlines, not quite streamlined, but it shows what the flow pattern looks like. We look here at the pressure distribution and velocity distribution along walls. As I said, walls are here not, there is no friction, so the slip at wall. So the velocity at the inlet cross-section is the same along the whole cross-section, same at the wall, 1 meter per second, constant at both walls, upper and lower wall. And then at the lower wall, the velocity goes down towards 0 and becomes 0 at the front stagnation point, as you can see on these small pictures with vectors. Then there is a very rapid increase in velocity, and it goes to 2.6 times larger velocity at the top of the obstacle. And then it drops again to 0, and here to something which is becomes also slightly negative in the down corner. And then it recovers. And you see here what is the numerical error. So ideally the velocity for the downstream should be the same as upstream. Should have fully symmetric solution, because we're using finite mesh. There are discretization errors, and that's why these two velocities don't match. Red line shows velocity around the top wall, and we see an increase in velocity to almost 1.8 times the inlet velocity, and then decrease. The mean velocity is twice the large, but twice the velocity at the inlet, so it would be 2. But we see that at the bottom wall it's 2.6, and at the top wall is 1.78 or something, and when you integrate, you will get the mean. The pressure distribution along walls is showing opposite trends. So you have 0 pressure constant at the upstream. There is no pressure drop along the channel, so straight channel in viscid flow, no pressure drop. Then there is a pressure drop along top wall, which is red line. As we approach the obstacle, the pressure reduces because velocity increases. So this is what I said, what the Bernoulli equation will also tell you. From invested flow, pressure drops, and then it increases again and comes in the straight channel path downstream to the same level as it was upstream. So the obstacle causes no pressure drop. You have only locally pressure dropping because velocity is increasing, but there is no energy loss, so further downstream you have the same pressure. On the bottom wall, you see what you can see also from the contours. First, there is an increase of pressure up to the stagnation point. Then there is a very rapid decrease along the curved surface. Minimum is at x equals 0, just at the top of the obstacle, and then there is again increase. And the maximum at the back should be the same as the maximum in front. It's not the same here because of the errors that I mentioned earlier. Now pressure comes to the same value as at downstream side as at upstream side, but the velocity doesn't. So discretization error here is manifested only in velocities, not in pressure. Okay, so that was a simple viscid flow. Now, when the flow is viscous and we have such variations of cross-sectional geometry, we will get other effects which are not seen in the viscid flow. In viscid flow sticks to the follows the wall. There are no separation, no viscous effects. But if we have viscous flow, there will be flow separation. This is an important feature of flows. And Prandtl, a famous name that you have to remember for fluid dynamics, Prandtl is as important as Reynolds. He worked a lot on turbulence also, and boundary layer methods developed. But he also looked at flow separation, and he stated the two conditions that need to be fulfilled in order for flow to separate. The one condition is that you have to have adverse pressure gradient. That means that the pressure is increasing in the flow direction. And if you remember Navier-Stokes equation, you see it contains the minus dP by dx, let's say. So if the pressure is increasing in the flow direction, that means that you have a force which is working in the opposite direction, it's acting in the opposite direction to flow, and it is tending to slow the flow down. And then the separation will only happen if another condition is fulfilled, and that is that there is a wall which is adjacent to the flow in the flow direction. And I will show later an example of the same flow with the same adverse pressure gradient, but in one case there is separation because there is a splitter plate added, and in the other case, if you remove the splitter plate, there is no separation because there is no wall. So the flow has to separate from a wall and reattach at the wall again. Now the reason for separation and reverse flow is that fluid near wall has a low velocity, so as soon as there is a wall there, and the viscous effects are taken into account, near wall, at the wall exact velocity is zero, and then if you have a flow along the wall, it will be slowed down near wall, and basically near wall fluid in general follows the direction of reducing pressure. And we will see later on also for secondary flows, in order to know what is the pattern of secondary flow, you only have to look at the pressure distribution. Near wall, the flow will go in the direction of reducing pressure. Further away from wall, fluid may have sufficient kinetic energy to flow against the adverse pressure gradient, because what then happens is the adverse pressure gradient will slow the flow down, but if kinetic energy is sufficient, you will be converting kinetic energy to pressure energy, but you may not have a reverse flow. It will still be in the same direction. So here is the picture that I mentioned. It comes from Hermann Fettinger, who worked in Berlin. There is now Hermann Fettinger Institute in Berlin. So in 1935, he made these pictures. So what you see here is the flow coming from left towards right, and the black thing here is an obstacle. It's a flat plate, which is put 90 degrees to flow direction. Now the flow that comes from left needs to go around this obstacle, and you have a stagnation point in the middle of the plate. And you see here on these flow visualizations that the flow goes up, then separates at the corner of this plate, and goes still further to the side, and then closes in a big separation somewhere behind the plate. But the question was here about the separation in front of the plate. And we see here that the pressure, if I take this blue line, which is the streamline along the center line of the plate, the velocity goes to zero, the red line goes to zero at the plate, and the pressure goes to maximum at the plate. So that's the stagnation point where the whole kinetic energy of the fluid that was flowing along this streamline is converting now to pressure and velocity is zero. Pressure is maximum. So we see here is the maximum pressure, and towards the edge of the plate, the pressure will be reducing. And that's why along the plate the fluid flows up from the center or down from the center, but there is no backflow because there is no wall here. On the right, a splitter plate has been added at the center of the plate here. So the black plate is the obstacle. The thin plate here is just to add it along this streamline here, which separates the part of the flow that goes above and part of the flow that goes below. And what you see now is there are recirculations here. There is flow separation on this wall of the splitter plate, because now you have almost the same pressure distribution as on the left, but now there is here a wall in the flow direction, and velocity is not zero only at this black plate here. The velocity becomes zero already at the beginning of the splitter plate, and along the whole splitter plate we have zero velocity at wall. And that means that the flow here is much more slowed down than on the left, and we get here this separation. And we will see it later on in other cases, but I find these visualizations from 1935, so 85 years ago, very nice. This is another example of flow separation which happens in diffusers. This now comes from Prantl and his co-workers 2 years earlier, from 1933. So you have here flow, it's like a nozzle which then expands the diffuser, and the flow simply continues straight, and you have here large separation on either side of this jet. And this separation can be symmetric or asymmetric. You can have larger recirculation on one side and on the other side. But what Prantl was showing here is that you can avoid separation by applying suction at these locations which are shown here by these small white marks. So if you suck the fluid there, what happens then is you create low pressure at the suction point, and this attracts then the fluid from the center towards the wall. And by applying the right amount of suction, you can actually bring the fluid to stick to the wall and not separate. And you avoid completely this separation here in the channel. So another possibility to avoid separation is to blow the high velocity fluid into the boundary layer, but then you have to blow it almost tangential to the wall, and then this high velocity fluid will then stick to the wall longer, and will also attract the other fluid to join, and it will also be possible to avoid separation. Okay, now the flow separation is in most cases undesirable, and a lot of applied CFD tasks are to find out, is there a separation? If it is, how big it is, and then you need to find out whether it can be somehow avoided. Why is it undesirable? Well, it increases pressure loss, and in that sense it increases drag on bodies. It can lead to vortex shedding, which then creates high lateral forces, so that can be dangerous for structural integrity of the flow domain. It increases flow unsteadiness, which can increase noise and vibration. And also it increases residence time of fluid near wall. And that can lead to reduced heat transfer and danger of overheating. So if you have somewhere a corner, like shown at the previous picture, when you had the splitter plate at the top, then this fluid recirculates for ages there. And if the wall is hot, this fluid will heat up to the temperature of the wall. So there will be, and if the purpose of flow was to cool the wall, then there will be very low cooling where you have recirculation. So that's something that's usually to be avoided. And now, can we predict flow separation? Of course we can. The the question is how accurately and at what cost. If the flow separation is pinned at a sharp edge, like this blunt obstacle that we had earlier, like a plate with sharp edges, then the flow has to separate at the edge, and that is captured well even with a relatively coarse grit. If you have a smooth surface, like a cylinder that I showed earlier, then flow separation is more difficult to predict. Laminar flow is usually, again, no problem, but turbulent flow is usually problematic. We can always predict it accurately if we use direct numerical simulation or large area simulation. You will hear in 2 weeks more about these methods, but they are too expensive and you can't use them for many practical applications. And other turbulence models, the usual weakest point is separation from a curved smooth surface. Now we shall study flow separation and circulation in several test cases. One is the channel with a semicircular obstacle in 2 variants that we have already seen. And then next week we will talk about diffusers and nozzles with different angles of contraction and expansion. And we will then look at features of the flow that can be encountered and how they can be simulated and with what accuracy. Now, in addition to flow features, we will also consider numerical efficiency, stability and accuracy, and we will vary grid fineness, we will vary under-relaxation factor, and we will also vary the type of analysis, steady or transient, to see how we get the results of the flow. Okay, there are a few other parameters which we will also address during this. So first, look at the laminar flow. As I mentioned earlier, Navier-Stokes equations are very good mathematical models, so modeling errors can be more or less neglected. We can predict them accurately with moderate resources. The flow remains in channels and pipes laminar up to Reynolds number about 2000 in practical applications. Transition to turbulence can occur earlier if the geometry is complicated or if walls are rough, if there are some separations which will then trigger unsteadiness and make the flow unsteady and so on. But also laminar flow can exist at high Reynolds numbers. For example, in a pipe, the highest Reynolds number in laminar regime that I remember reading about was larger than 100,000. But that was a special laboratory with some special tables which are such that they are disconnected from any disturbance, any shaking or whatever from the background and so on and so on. So very complicated experiments. But then the smallest disturbance, if you say loudly a word, the flow will immediately turn into turbulent because it is simply very prone to react to instability. So I don't know how it's English name. In German we will say labil. It's like if you have a ball on a hill, you know, you put a ball on top of something curved, and if you're very careful, you may find a location where it will stay there, but it will roll left or right if you disturb it just a little bit. In channels and pipes, laminar flow results in pressure losses, as we said earlier, friction at walls and geometry changes, and this is something that we will then look at in simulation. So first example is laminar flow in a channel with a semi-cylindrical obstacle at the bottom. So this is, you have wall at the top, wall at the bottom, and it is like you take a half a cylinder and stick it to the bottom wall, so you are now constricting the cross-sectional area by a factor of 2. So this is the same example that I use for invested flow. Only if you compare now pressure distribution here at the Reynolds number of 100 to invested flow, you see a huge difference. The front part is similar. You have maximum pressure at the front stagnation point, and then you see a rapid decrease of pressure, and the minimum is somewhere close to the top of the obstacle. But then on the back, you see a large zone of almost constant pressure. And then pressure first increases gradually, and then later on, further downstream, you will get again channel flow in which pressure decreases. And we see also at the top wall that the minimum pressure is now not above obstacle, but somewhere further downstream. So maybe half or more than half of the obstacle width further downstream. Now we will look at this pressure and velocity distribution in more detail later. Let's first look at the velocity vectors. And what you see here is that the flow accelerates along the obstacle on the upstream side. And then, because the flow now is much faster, it cannot follow the curved wall downstream. It simply separates. It goes kind of straight, not quite straight, but a little bit further down to the middle of the channel. And you may also get separation at the top wall behind the obstacle, but there are two separations on the obstacle. One is the large separation behind, and there is also a small separation at the front stagnation point, because we have now wall here where we have adverse pressure gradient. As Branto said, this is a condition where separation happens. But because this is a laminar flow, you cannot see velocities here. They are so small. But these lines here below, they do indicate that there is a recirculation. We will see much larger recirculation in turbulent flow for the same situation. If we now look at the shear stress at the wall, so let's take first the upper wall. We follow the wall from the straight channel. In the straight laminar channel, shear stress is constant. I started at fully developed flow at inlet, so I specified analytical solution, which I know for this 2D flow. Basically, it's two-dimensional in the sense that the front and the back are here considered symmetry planes, so it simulates an infinitely long obstacle and channel in the cross direction. And then shear stress increases, and we have at the above obstacle somewhere shear stress which is something like 5 times larger than, or 4.5 times, well, it's more, it's almost 5 times larger than in the straight part. And then the shear stress decreases, and further behind, it becomes much smaller than in the straight duct in front, less than half of it. And then it recovers, and somewhere further downstream, we will have the same shear stress in the fully developed flow as we had upstream of obstacle. But this takes now longer distance, so I didn't compute long enough. But let's say it would be a 1 meter further downstream when you get fully developed flow again. If you take the bottom wall, then we see first decrease in shear stress, and it becomes zero where the recirculation begins. But we see the recirculation very tiny, and then we have a finite shear stress in the opposite direction, which we can't see. Then along the obstacle, the shear stress increases, and it becomes more than 8 times higher than in straight channel at the top of the obstacle, somewhere around the top. And then again, it goes to zero behind. Then it changes sign, but we are plotting here magnitude, so you don't see the sign change. And then there is again zero value. Then there is again change of sign, and then there is last zero value. So this last zero value near x equal 0.3, that's where the bigger circulation ends. And this 1 0 before is there are two recirculations here in the opposite directions. But as I said, because of weak flow, they are not visible. So you see that now flow pattern near bottom wall and top wall are totally different because of the difference in geometry. If you look at pressure variation, it's now different to invested flow. We see first in the straight part of the channel upstream of obstacle linear pressure distribution, the same pressure at the top and bottom wall, so blue line and red line are the same. And now there are differences. Now as we approach the front stagnation point on the obstacle, the pressure first increases, that's what the blue line shows, increases a little bit rather than decreasing. The light blue line shows what the pressure would look like without obstacle. It would simply continue linearly downstream. Then there is a pressure, sudden pressure drop along the front side of the obstacle with the minimum somewhere just a little bit behind the top of the obstacle. Then there is an increase in pressure relatively rapid. And then here is where the blue line again comes close to the red line. The red line shows on the top wall that the pressure then starts decreasing faster than this linear shape in the straight channel, goes below goes to some low value and then increases over a certain part, because you now have something like a diffuser behind the obstacle where the cross-sectional area increases and the velocity will be decreasing, pressure should be increasing. So this is a little bit of Bernoulli that stayed there. And then somewhere further downstream at around x equal 0.5, both pressure at the top wall and bottom wall will be starting decreasing, and after a while we will achieve again the laminar linear pressure decrease for a fully developed flow. So the slope will become parallel to the slope that you would have in an undisturbed channel. But now we see what is the additional pressure drop due to obstacle. Further downstream we will have again linear profile, linear variation of pressure, and all this disturbance that is caused, the first increase and decrease and again increase around the obstacle, this will later on be forgotten, but there is this additional pressure drop due to obstacle which is not forgotten, and this is what will be now the local loss. So if I was using 1D models, I would have a straight duct, but I would have had here an element which has a local loss, which will have to produce the pressure drop of this order. Only that in the one-dimensional analysis you will simply have a pressure drop at a single point or single element and continue with the straight duct again. But as I said, this additional pressure drop, this local pressure drop due to obstacle, you cannot simply determine it without either doing experiment and measuring the pressure along the walls or doing a simulation. And this, in this case, could be done with simulation. Now, let's look at computational efficiency. Many codes have default under relaxation factors, 0.7 for velocities, 0.3 for pressure. And if you use the so-called segregated solution method, it starts as in plus, and you would see this behavior for one grid. 0.7, 0.3 combination for pressure and velocity has some initial quick decrease on the residuals, done flat part, and then later on decrease at a constant rate, but it will take long to reduce final. Okay, so in this picture we dropped the residuals almost to 10 to minus 4, though this is sufficient, but by doing the same number of iterations with a different set of under relaxation factor, 0.8 for velocity, 0.2 for pressure, we will reduce the residuals almost 7 orders of magnitude. And by increasing the under relaxation to 0.9 for velocities and reducing for pressure to 0.1, we will get 10 to minus 7 reduction of residuals in 300 iterations. So you see a significant increase in efficiency by increasing the under relaxation factor for velocity and decreasing for pressure. And between 0.8 and 0.9, the factor in efficiency is 2. You need twice less iterations. And you see that if you use default values, it takes longer. Now, why are default values so conservative? Well, for other flows, and especially when they're turbulent, for more complicated geometries, you may not be able to get solutions with 0.9 under relaxation for velocities, and maybe even not with 0.8. Although I always use at least 0.8, 0.2, because in most cases it works. Now let's see what happens when we refine the grid. And here refinement was by a factor of 2, so grid spacing in every cell was subdivided in 2 in each direction. We see basically the same behavior. Combination 0.9, 0.1 is twice as fast as 0.8, 0.2, but what we also see is that we need twice as many iterations to reach the same residual level as on the coarser grid. So here, if we take 0.9, 0.1, we need 600 iterations to go to 10 to minus 7, which is more than necessary, but And if we look at the coarse grid, we needed 300, so twice as much. Okay, in some codes, in Fluent and in CFX, in Stasis in Plus, you have also coupled solver, which solves for velocities and pressure and temperature as one vector of unknowns. And there you don't have under relaxation, but you have CFL number, which is basically you're doing steady state analysis, but it's doing marching in a pseudo time, some false time. And this CFL is the Courant-Friedrich-Levy number, which means how far the fluid goes within one time step. And CFL 10 means the fluid moves 10 cells within one of these false time steps. Now, default in many codes is CFL 5. That's also Stasis in Plus. But this is highly inefficient for laminar flows. Now, it may be okay for some high-speed supersonic flows, it's fine, often, but for laminar steady-state flow, it's far too inefficient to do a simulation with that CFL number. So I did CFL 10, CFL 100, and CFL 1000. And the 10 is far too slow. And between 100 and 1000, you have again a large factor. And you can even go to 10,000, I think, for this flow. Maybe not exactly, but very close. If I refine the grid by a factor of 2, I see more or less the same thing as before, which is that you need twice as many iterations to reach the same residual level. So we see here 100 was enough for 10 to minus 7. Here, with fine grid, we need 200. So that gives you the feeling. As you refine the grid, you need more iterations to reach the same convergence criteria. Now, you need per iteration more computing time. And if the number of iterations was the same, then computing time will be proportional to the number of cells. But because also the number of iterations increases, then the computing effort for finer grids is over proportional. And a perfect multi-grid method applied to outer iterations that I mentioned last time, that will have a constant number of iterations. And the solver in CFX software that's part of ANSYS offering, which is not further developed but is available still, that has a multi-grid method applied to outer iteration, and that would have here the same number of iterations for every grid. So computing time would be proportional to number of cells. But of course, this is only for steady flows. For unsteady flows, usually the convergence doesn't affect so much, is not affected so much by the grid. When you refine the grid, you have to reduce the time step. That's why to keep the same Courant number, and that's why then computing effort still increases over proportional. Okay, so steady laminar flows can be computed faster using coupled solver than a segregated solver is used if an optimum CFL parameter is employed. The problem is that this optimum varies in a very large range, from 1 to 10,000. Default is 5, which is inaccurate. In a segregated solver, one varies under relaxation. The range is much narrower, typically between 0.7 and 0.9. But if you take it too large, then it will diverge. So one has to be careful. Coupled solver needs more memory and computing time per iteration, roughly 30%. But its efficiency on parallel computers is higher because there is less communication events than in segregated solver. Segregated solver solves for every velocity one after the other. So you have communication between processors for U, and then you have communication for V and for W and for pressure. In a coupled solver, when you communicate all variables, velocities, pressure, and temperature. So there is 5 times less events if it's with temperature variation, and that means less communication, and that's why parallel efficiency is high. So if you see simulations on a very large number of processors, coupled solver is more efficient. But as I said, this Double solver has only advantage for steady flows. If we take now, instead of obstacle on a wall, a cylinder between two channel walls, then we can do the simulation two ways. One is by using a symmetry plane and computing only half, and the other one is using the whole geometry. Now the problem here is that the flow is symmetric only for the Reynolds number up to 50. So the separation will be steady up to Reynolds number 50. After it becomes unsteady, and you get asymmetric flow. So you can still solve it with symmetry condition. You will get a steady state for a longer period of time, but it is then not the flow that you will get in reality. Although in principle, Navier-Stokes equations, as I said, they have also a symmetric solution for this geometry, but you can't get it in experiment and you can't keep it in simulation if you have the whole geometry. The smallest round of errors in the simulation will trigger asymmetry and the flow becomes unsteady. But let's first see what we get if you apply symmetry. Then you get flow which looks like this. It's very similar to the flow with the obstacle on the bottom wall, but the difference is that you now don't have separation at the front stagnation point because there is no wall. As the Prandtl said, no wall. In spite of the adverse pressure gradient, it looks the same as in the case of wall at the bottom. Now it is symmetry, there is no separation. And then this large zone here of almost constant pressure behind the obstacle is still larger. If I now try to solve the flow as steady for the full geometry, having no symmetry plane but cylinder between two walls, this is the picture of residuals that you get. The residuals, when you start with constant velocity, they first reduce, then they wobble a little bit around, then they start increasing and stop at a level of 0.2. They will not, the simulation will not diverge, but the residuals will then oscillate at this level forever. You can iterate as long as you want. And the reason is that the flow is by nature unsteady. There is vortex shedding behind cylinder, and you can't get steady state solution. So simulation will not diverge, but it will never get a solution. So because the residual is so high, even though when you plot the vectors like I did here, it looks like a